Good morning, everyone. I am Steve from Computer Science and Engineering Department, Karunya. I am going to explain about full adder and half adder logical circuits today. Now we can go into the explanation. Now I am going to explain about the full adder logical circuit. Here it's the truth table for the full adder logical circuit, and it consists of 3 variables and 1 carry off and 1 sum. Now it's the x, y, and z is the common variable for 0, 0, 0 and 0, 0, 1 and 0, 1, 0. It has totally 15 constraints here. And now here we have the carryover and sum, like 0, 0 and 0, 1, 0, 1, and here. Here we have the formulas for that. Now we can derive the formula from the truth table right now. Now we can derive it for the S as sum. First choose the ones place here. The 1 consists of here 0, 0, and 1, which is nothing but x dash, y dash, and z. Plus the other one carries of 0, 1, and 0, which takes the x complement, y, and z complement, plus the other one as 1, 0, and 0, which is nothing but x, y complement, and z complement. And the last one represents of 1, 1, and 1, which takes the x, y, and z. Okay. Here we get the equation as x complement y complement z plus x complement y z complement plus x y complement z complement plus x y and z. Now we are substituting it through normal substitution method. Here we are taking x complement as common, hence we are getting it as x complement into y complement z plus y z complement, and here we are taking it as x as common. So here we are getting it as y complement into z complement plus y z. Now look here, y z complement and y complement z, it's nothing but as y XOR of z. Now we are converting that formula into y XOR of z, and here we are taking it as y complement z complement plus y and z, which is nothing but as y x nor of z, and it is also known as in the way of y XOR z the whole complement. Now here it is representing as the same way, which is nothing but the x complement y XOR z plus x y XOR z the whole complement here. Hence we can conclude it by saying it as x XOR y XOR z. Now we are getting the formula here for the sum. In the same procedure, we can do it for the carryover right now. Here we are taking this one and this one and this one and this. So hence we are confirming this with the x, y, and z variables as 0, 1, and 1, which is nothing but of x complement y z plus the other variable for that 1, 0, 1, which is nothing but as x, y complement z plus the other variable of it 1, 1, and 0, which is nothing but as x, y, and z complement, and the last variable which represents of 1, 1, and 1, which is nothing but x, y, and z. Now by the same procedure we can go into this. In this carryover equation, we are taking this z as common for the first set of variables, and in second set we are taking this x, y as common. Hence we are getting the first equation as x complement y plus xy complement into z, which is nothing but it is in the form of x XOR of y. So we can conclude that by saying x XOR of y into z. And here we gets as xy into z complement plus z, which represents as 1. Hence it results in x and y. Now we got the answers for carryover and sum. With the same procedure, we can go on to the full adder logical circuit here. Now we are consisting of first x XOR of y, which is nothing but here we are having the XOR gate and 2 constraints of x and y is passing through it. So here we getting that x XOR of y, and again we are having another XOR gate here which constraints of z and x XOR y, which represents as x XOR y XOR z, so that we are getting it as yes. And again in the same format of C, First, we are taking it as X XOR Y from this same circuit, and we are adding it to another AND circuit with Z. So we are getting it as X XOR Y into Z. And in the same way, we are taking it as X and Y into the another AND gate, and we get two outputs now, X XOR Y and XY. Now we are merging these two into another OR gate to represent this plus symbol. So we are getting the same formula of X XOR of Y Z plus XY, which is nothing but the carryover here. Yeah. Now we can go to the full subtractor procedure. It's nothing but it is in the same way of the full adder. But here it is given as, instead of sum, we are using difference, and instead of carryover, we are using borrow. Others are all in the same format of that. Now we can calculate the formula for D using the truth table. Now we can take off all the ones place here, which is nothing but as 0, 0, 1 plus 0, 1, 0 plus 1, 0, 0 and 1, 1 and 1, which is nothing but as same of the S. It's X complement Y complement Z plus X complement Y Z complement plus X Y complement Z complement plus X Y Z. It's giving the same equation of the sum, which is nothing but X XOR Y and Y XOR Z. Hence we got the equation of difference. Now we can move on to the borrow equation. Now look at the borrow of truth table. Here also same way, take all the ones place here, which is nothing but 0, 0, 1 plus 0, 1, 0 plus 0, 1, 1 plus 1, 1 and 1. Hence we are representing in the way of X bar Y bar Z plus X bar Y Z bar plus X bar Y Z plus X Y Z. Now we are taking here it as X bar as common, and we are getting it as Y bar Z plus Y Z bar, which is nothing but as Y XOR of Z. Hence we are concluding in that way, we are getting it as X bar into Y XOR of Z. Now in the same way, we can take in the second set of the equation as Y and Z as common. Hence we are getting it as X plus of X complement, which is nothing but as 1, which returns the same value of Y and Z. So we get the formula for borrow as X complement Y of X or Z plus Y Z. Now with the used formula, we can go to the logical Gird circuit. Now we are taking it as switches for again the same X, Y and Z here. Now for using the difference here, we are first inserting the Y XOR gate here. This is an XOR gate which consists of Y and Z and gets an output of Y XOR of Z. Now here in the same way, another XOR gate passes through here, which is X as one input and another input as Y XOR Z, which gives the formula for D, the difference. And in the same way of borrow, we are getting it as, we are passing an AND gate through the X naught and Y XOR of Z. We are taking the formula from the previous circuit logic. And we are constraints of another of Y and Z through an AND gate to represent that Y dot Z, which is again consisting through passing through an OR gate to represent as X bar Y XOR plus Y and Z, which gives the formula of B. Now we can go to the truth table verification. Yeah, we can take anything it as, for the first thing itself, 0, 0 and 0, which represents the carryover and sum as 0, where the bulb doesn't glow here in both the places of S and C. Now we can randomly choose a variable of 0, 1 and 0. Yeah, so I'm setting it as X as 0, Y as 1 and Z as 0, which gives me the output of S as 1 where the bulb glows. So we can check it here. The 0, 1 and 0 gives the output of 1 here, and the carryover represents 0, so the bulb doesn't glow in the C place. So in the same way, we can take it as X as 1 and Y as 0 and Z as 1, so that now the S bulb turns off, which represents 0, and C bulb glows due to just 1. Here we can check the variable with the truth table as 101, which represents as carryover as 1 and sum as 0. Now, for making everything is glowing, we are using the last truth table value of 1, 1, and 1. We are making here x, y, and z all the three as 1. So we can see here both the bulbs are glowing. Like in the same way, we can go to the full subtractor. Here also it consists of three variables. We can take any variable like 0, 1, and 0 I'm taking here, like x as 0, y as 1, and z as 0, where we can see the D bulb and the B bulb also glowing in the same way, where we can check through the truth table, which also represents 1 and 1 here. Again, to the next step, we can see the truth table by 1, 0, and 0. We are keeping x as 1, y as 0, and z as 0, where the D bulb glows, and here we can see that D as 1 and the B as 0. Like another way we can take only the B to glow is 0, 1, 1. I'm taking x as 0, y as 0, and z as 1 to make the both the bulbs glow, D and B bulb glowing here, which represents that 1 and 1. Now I'm gonna take it as 0, 1, and 1, which is nothing but I'm taking it as x as 0, y as 1, and the z as 1, where the B bulb alone glows and the D bulb doesn't glow here. It represents the D as 0 and B as 1. Hence, it is verified through the truth table, and both the logical gates of the adder and the subtractor logical gates confines with the truth table of x, y, and z in three variables. Now we can see the half of the product of this by moving to half adder and the half subtractor, which is nothing but the half of the format which consists of the two variable of that. Now we can move to that. Now we are going to half adder and half subtractor here. First, we will be seeing with half adder. It's also the same way, which consists of a carryover and sum, but it consists only of two variables. So it has only two inputs here, which is consist of x and y. We are mapping it with 0, 0, 0, 1, and 1, and 0, and 1, and 1 with the same truth table format here. Now we are getting the output as sum as 0, 1, 1, and 0, and carryover as 0, 0, and 1. Now for getting the formula of the sum here, we are taking all the one variable here. Hence we are getting it as x as 0, y as 1, which is nothing but x, y complement plus, and the other variable of 1 and 0 is x complement of y. Yeah. Hence it represents in the same way of x XOR of y. Hence it gives in the same value to sum, which represents the half of the full adder. So in the same way, we can check the carryovers formula here by representing here it is only one variable is represented, which is in x as 1 and y as 1, which is nothing but c is equal to x and y is the formula for that. And now going to an half subtractor here, it represents as d as 0, 1, 1, and 0, and for borrow it is 0, 1, 0, and 0. Moving in the same way, we represent here it also. For calculating the formula of the difference, we are taking out the one variable here, that is x as 0 and y as 1, which is nothing but as x bar of y, and another variable as 1 and 0, which is nothing but of x and y bar, which represents the same formula of x XOR of y. And for borrow, we are having here the 1 point is nothing but 0 and 1, which represents the x bar of y. So now we can verify these with the truth table values here. Look, I'm taking x and y, both the values of 0, so the bulb doesn't glow in x, either in the y. So we can conclude with that it is 0 and 0. Now I'm changing the value of x as 0 and y as 1, where we can see that S as glows. Look here, 0 and 1, when I take the sum value has been represented as 1 where the bulb glows. And in the same way, when we take y as 0 and x as 1, we can see the same S bulb glows here. 1, 0, which is represents the one variable here. And when we take both the variables as on, the variable gets 0 in sum. So the bulb doesn't glows in S, but we can see here the C bulb glows. So it is representing here 1. Hence the truth table for the half adder is verified. Now we can go to the half subtractor value now. Now the same value here, I am giving it as x as 0 and y as 0. So we are getting the both the values as 0 and 0. When I switch on y as 1, here we can see it as 0 and 1, where the both the bulbs glows, D and B, which is nothing but the difference and the borrow bulb glows here, which is representing it as 1 and 1 variable. Again, when I switch it x as 1 and y as 0, the only the D bulb glows here. So we can check with the truth table here, 1 and 0 represents as difference as 1, but there is no borrow section here. The same with when we have the both the variables of on in one variable, like x and y are 1 and 1, we get the both the outputs as 0 and 0. So the both the bulb doesn't close. Hence it is also verified with the same truth table, and the half adder and the half subtractor are also verified with the truth table, and it's just the half of the full adder and full subtractor logic gates. Yeah, thank you.